Hello everyone. Today we're going to talk about a concept called equilibrium. So this is going to lead us into something called Le Chatelier's principle, which is a bit of a tricky topic, so we really want to make sure we understand this before we get into that. Of course, there's the morning bell, right? So first off, let's review something that we talked about earlier on in this unit. We talked about rate of reaction. So remember what that is. It's how much substance is used up over time. So the speed at which that reaction is occurring is how much reactant we're consuming. So how much we're using up over a unit of time, so how quickly or how slowly the reaction is progressing. So at equilibrium, clearly there's a word equal here, so something is equal. So remembering what is equal is really the important part. So what's equal is the rate of the forward reaction equals the rate of the reverse reaction. So that means the speed that the forward reaction is occurring is equal to the rate of the reaction going in the opposite direction. So the rate of the forward reaction equals the rate of the reverse reaction. So we'll talk about that and I'll give you some analogies to try and help you understand this. So the concentrations, meaning how much of the substance is involved in the reaction, do not have to be equal, but what they are doing is they're staying constant. So this last bullet is really one of the important ones that you want to remember. What does constant mean? We're not changing. So at equilibrium, you want to keep saying in your head, rates are equal, concentrations are constant, meaning they're not changing. So star that, whatever. So if you want to take notes as we're going throughout this, or if you want to print out the notes and look along, but you know, whatever you want to do is up to you, but if you take notes along with this as if we were sitting in class, that's a good idea. I'll go through this lesson just like a regular lesson in class, and we'll see how that works out. All right, so let's look at a reaction. Here's a simple reaction. So carbon plus oxygen makes CO2. So this arrow here is what's showing us that we're dealing with a reversible reaction. So we call this a reversible reaction. It can go forward and it can go backwards. All right, so these are the types of reactions we're going to be dealing with when we're talking about systems at equilibrium. This is a different type of reaction, but notice we only have one side on that arrow, right? It's only going one way. This is like a one-way street. This type of reaction can't reach equilibrium. It just goes until reactants run out. So it's going to keep going until we run out of magnesium and hydrochloric acid, and then the reaction stops. So we're not going to be dealing with these reactions here. We want to have these reversible reactions. All right? So here's my analogy of what we're talking about when we're dealing with equilibrium. So here's a bunch of happy students in the classroom. You guys aren't here right now. I'm sure you wish you were. You'd be that excited as my little emojis up here. And then here's a couple of students out in the hall. All right? So now let's say every minute a student leaves the classroom, but every minute one student enters. What's going to happen to my amounts of students in the classroom and in the hall? Right? Every minute a student leaves, every minute a student comes in, and if this keeps going on, look what happened. Didn't change. My number of students in the classroom is the same as my number of students out in the hallway. This is what we call a system at equilibrium. Rate of the forward reaction equals the rate of the reversible reaction, so there's no observable change. All right? So why is that happening? Because the rates are equal. The speed at which the students are leaving equals the speed at which the students come in, so there's no observable change. Okay? So, and notice the concentrations are staying constant. Not equal. We've got 9 students in the classroom, 4 in the hall. Not the same, but they're not changing. That's what we mean by constant. Okay? So, they could be equal. It just doesn't matter. They don't have to be. It's irrelevant. All right? So now, let's say every minute 2 students leave the classroom, but only 1 student enters. Now, think about what's going to happen. If 2 students are leaving and 1 student is coming in every minute, think about how that's going to affect our amount of students in the hall versus those in the classroom, right? If more students are leaving, we're going to start to get what we call shift in this direction. So let's watch this take place, right? Look, here we go. Hey, 2 students are leaving, 1 student comes in. 2 students leave, 1 student comes in, 2 students leave, and notice as this goes on, now look what happened. Now we have more students in the hall than we did in the classroom. So we got what we call a shift, right? We had a shift right. Keep that in mind because we're going to be using these terms again as we go through the lesson, all right? So we're going to shift right. So this is a system that is not at equilibrium. So the rate of the forward reaction is not equal to the rate of the reverse reaction. So we saw a change in those concentrations. So we had an observable change. Now there's more students in the hall and less students in the classroom. So this is a system that's not at equilibrium. So let's talk about some types of equilibrium. First we have physical equilibrium. So this is dealing with the phase change generally. So physical, it's not chemical, we're just phase changing is one type of physical change. We talked about that way back in the beginning of the year. So we'll use water evaporating or vaporizing as our example. So here's a closed system. So now you have some water, and then we have water present in the gas phase as well. So water, liquid H2O, vaporizes, goes into the gas phase, but we also have gas H2O condensing back into the liquid phase. So this process is happening in any sample of water that you have, your water bottle, whatever. So when we're at equilibrium, the rate of evaporation is equal to the rate of condensation. So when you have your water bottle just sitting there capped, you ever notice when it gets like kind of warm out or whatever, if it's sitting there for a while, you'll see some condensation building up towards the top of the water bottle. That's because this process is occurring. The water is evaporating, but then it's also recondensing and going back down into the liquid phase. So when we're at equilibrium, the rate of evaporation equals the rate of condensation, and we don't notice any changes at all. The volume of water stays the same. The amount of gas that we can't see is staying the same as well, and we don't notice any observable change, right? That's a physical equilibrium. So another type of physical equilibrium is a solution equilibrium. So all you really need to know is a saturated solution is the only time at which we're at equilibrium, right? So saturated solution when the rate of particles going into solution equals the rate of particles coming out of solution. So that's what a saturated solution is, when the forward reaction equals the reverse reaction. So our reaction here is simply just NaCl dissolving. So the rate at which the NaCl is breaking up into sodium and chloride ions is the same at which those ions are coming back together and forming NaCl. So that's all you really need to know. The only type of solution that's ever at equilibrium is a saturated solution. All right? Only type of solution at equilibrium. That's all you really need to know. Right? Saturated solutions are the only types of solutions that are at equilibrium. So now, chemical equilibriums are really what we're going to spend the rest of our time talking about. So this is when the concentration of reactants and products remain constant. We talked about that before. Why? Because the rates are equal. And if the rates are equal and the concentrations aren't changing, there's no observable change, right? But remember, this reaction never stops. All we do is we get back to an equilibrium, right? We get back to an equilibrium, which means the rate of the forward reaction equals the rate of the reverse reaction, right? So, but it never really stops. All we're really doing is getting back to our equilibrium. So there's certain things that are going to happen that are going to cause one direction reaction to speed up, slow down, whatever. But the goal here is always we want to try and get back to equilibrium. So that's when we get with Le Chatelier's principle. So here's the definition. It's a little wordy, but we'll talk about this as we go. What is Le Chatelier's principle? If a change in conditions, which we call a stress, is imposed on a system at equilibrium, the position will shift in the direction that reduces the change. So that's key here. Our goal is to reduce the change.